Welcome to Module 5 of Sustainability and Ecosystem Health, where we will define connectivity and resilience and discuss how managing connectivity can contribute to increasing resilience. The focus will be on ecological connectivity and a case study will be presented. Ecological connectivity is defined as the unimpeded movement of species and the flow of natural processes that sustain life on Earth. Connectivity is essential for ecosystem function and a vital element in the diversity of nature. It is vital that connectivity is maximised, as animals and plants rely on these connections for survival. It supports genetic diversity, and it will be crucial into the future as climate change challenges develop across all biomes and scales. Biodiversity decline has resulted from overexploitation of resources and habitat fragmentation. This in turn has decreased the connectivity that is imperative to the maximisation of diversity. Connectivity can be managed using a people-driven approach known as connectivity conservation. The main aims of connectivity conservation are to maintain, enhance and restore connectivity. Effective connectivity conservation can be used to promote biodiversity, to safeguard habitat, and to improve ecosystem functions such as migration, pollination, nutrient cycling, and climate change resilience. Resilience is defined as the capacity of a system to absorb disturbance and reorganise while undergoing change so as to still retain essentially the same function, structure, identity, and feedbacks. If connectivity is managed appropriately, the resilience of a system will increase. There are 4 aspects that are crucial to resilience. Number 1. Latitude is the amount a system can change before thresholds are crossed and the system goes over the tipping point. Number 2. Resistance is the ease or difficulty with which a system can change. Number 3. Precariousness is how close the system is to the tipping point or its limits. And number 4. Panicky, where the phases of adaptive cycles of systems, nested above and below, influence the resilience of the studied system. Let's examine a study of the Moreton Bay Marine Park, where the resilience of a system increased as a direct result of effective experimental management strategies, increasing connectivity in the area. The results of the 14-month study were very positive. The park was examined to determine the effects of connectivity on herbivorous fish, benthic assemblages, and ecological resilience. The study focused on 5 locations, including 1 protected reserve and at least 2 reefs, one within 250 metres and another over 500 metres away from a mangrove forest in each area. Large PVC tiles were placed on the sea floor, and half of these were contained within aluminium and monofilament cages, so that coral and algal growth could be measured with and without herbivorous fish access to quantify benthic succession. Herbivorous fish play a leading role in removing algae in the benthic zone. Removal of algae supports coral growth and enhances reef resilience, so healthy herbivorous fish populations should be encouraged. Results of this study supported links between connectivity and resilience. Results showed that reefs close to the mangrove forest supported approximately 4 times as many fish as those distant from the mangroves. This had a cascading effect on benthic succession and composition, with tiles closer to mangroves and in protected reserves supporting a greater diversity of organisms. Uncaged tiles that the algae-eating fish had access to supported a more diverse assemblage of algae and soft corals. Caged tiles had a much simpler assemblage of only 2 types of algae. This supports the theory that higher herbivorous fish densities removed more harmful algae and allowed higher densities of soft corals. The connectivity of the reefs to the mangroves positively correlated to higher herbivorous fish biomass, which in turn supported enhanced growing conditions for benthic zone organisms. This enhanced coral recruitment supported reef resilience. Findings of this study showed that when adjacent habitats and reefs are managed holistically and as a connected system, ecosystem resilience can increase. Managing the reefs and surrounding mangroves as one connected system has a positive impact on fish numbers and benthic zones and increased reef resilience. Managing connectivity must be done with caution, however, as enhanced connectivity via approaches such as ecological corridors can exacerbate the spread of weeds and diseases, although past studies show that response to disturbances is more effective and predictable in well-connected systems. A well-connected system reinforces resilience against stresses that affect individual parts of a system, and increasing system resilience aids in overcoming disturbances and assists with a more rapid recovery after a disturbance. Although managing connectivity can be challenging because of the positive, nonlinear relationship between connectivity and ecosystem function, overall well-connected systems have shown more resilience than less connected systems. Vulnerability within systems can be countered by effective management of connectivity to ensure that the system is well connected, has increased resilience, and has a good chance of minimal disruption from disturbances. Thank you.